This is a review of memory systems, caching, memory technology, and virtual memory in preparation for the second exam in Comp 375 at North Carolina A&T State University. The second exam is Wednesday, March 18th from 11 a.m. to noon. You've got to be logged on to Blackboard at that time. The exam ends at noon. Be ready for it. It will be an online exam. The topics of the second exam include memory types and caching, which we will discuss in this review. These cover chapters 5 and 6 of the textbook. Also covers digital logic, VLSI, and microcode. If you actually read the book and there were topics in the book that we didn't cover in class, they won't be on the exam. On the other hand, if we covered it in class, it certainly could be on the exam. You can logically consider memory to be in 4 different groups. The program instructions include the machine language of the program. Then we have global data, that is constants and other global variables that exist in the program. There are fixed locations. And then there's the heap in the stack. The heap contains dynamically allocated memory items. Every time you go new, then it creates memory in the heap area. The stack is used for parameter passing and for local variables. In the Intel world, the heap grows upwards, starts at some fixed address and gets bigger and bigger. The stack starts just below that and grows lower, so as you push something on the stack, it's at a lower address. There are several characteristics of memory technology. Primary memory includes the RAM and the cache. Secondary memory are devices that you access through I/O commands, such as disk drives. Right now, we're talking only about primary memory. Random or sequential access deals with whether you can access any particular location in memory with approximately equal time, or whether you have to go through it sequentially. Sequential access is like a tape drive, and we will generally not speak of the tape drives. The granularity deals with what size unit you can read or write. RAM and cache, you can generally write a byte or maybe a word, whereas larger units, such as disk drives or flash memory, you can access only in larger blocks. Volatility indicates whether the memory will lose its information when the power is removed. When you turn the power off your laptop, the RAM and the cache are all zeroed out. Except you don't want the disk drive to be zeroed out when you turn off the memory. So some memory has to keep its information while others can be cleared. RAM and cache can be changed during the execution of the program, whereas other parts of your memory you may want it to be read-only. The BIOS of your system is read-only. There are 2 basic technologies for the internal memory of your system: static RAM and dynamic RAM. Static RAM is used in the cache, and it's very fast. It consumes more power than other systems, and therefore creates more heat. It takes 4 to 6 transistors to implement static RAM. It's basically 2 NOT gates feeding back into each other. You can look at it from the transistor level and see that each NOT gate is made out of a NPN transistor and a PNP transistor for a total of 4, and then there are 2 other transistors for input and output. Dynamic RAM stores the data in a capacitor charge. It only requires 1 transistor per bit. It uses much less power because once you charge up the capacitor, you don't need any additional power to let it stay. Although it does need to be recharged after a while because the electricity will fade away. You can view a diagram of the dynamic RAM something like this. Although this diagram shows a separate capacitor, the capacitor is actually part of the transistor. And so when you turn on the address line, you can charge up the capacitor and fill it full of electrons or drain it out. Later, if you want to know what the value is, you open the address line and see if those electrons come out. If they come out, then it was stored up as a 1. If nothing comes out, it must have been a 0. Because the electrons come out, though, you have to fill it back up after you read it. You do not have to write static RAM again, only dynamic RAM. Dynamic RAM needs to be refreshed. The capacitor eventually loses charge over time. Not a really long period of time, just but milliseconds, not nanoseconds. So as you charge it up, the power will generally fade away. If you don't do anything, it'll fade to 0, and then you won't be able to tell the difference between a 1 bit and a 0 bit. So the systems will refresh the memory, reading it every now and again, and then if it was a 1, filling the transistors, capacitors up to full power. And so later, if you read it, you'll be able to know how much power was in there. You can compare the two internal memory types, static and dynamic RAM. Static RAM has 6 transistors, whereas there's only 1 transistor for dynamic RAM. Therefore, you can put a lot more dynamic RAM on a chip than static RAM. The static RAM uses a lot of power and therefore creates more heat than dynamic RAM. Static RAM doesn't require refreshing, but you have to refresh dynamic RAM. Dynamic RAM has to be rewritten, after you read it. Therefore, the reads take longer than a write. There's no difference in static RAM. And static RAM is generally used in your cache, whereas dynamic RAM is generally used for your RAM. A high-performance computer system, Cray computers, used to use static RAM for all their memory. Cray's supercomputers were built with the concept of, we don't care what it costs, somebody will buy one if we make the fastest computer in the world. So they used static RAM everywhere. It generated a lot of heat, and their systems were liquid cooled. Read-only memory can't be changed during the execution of the program. Sometimes they can be changed through extraordinary levels. The input-output system of your computer, the BIOS, is written in RAM, so it stays there when you turn off the computer. When you start your computer, it starts executing the program that's in the read-only memory. And that's how it boots itself up. Flash memory is a popular form of non-volatile memory. Flash memory can be read on an individual byte basis, but you have to write it in blocks. You have to flash to erase the blocks, and then you can write on it. It's used a lot for thumb drives or solid-state disks, which are replacements for disk drives that use flash memory chips instead of having physical rotating disks. Here's a summary of the different memory types. Cache memory is a high-speed memory that keeps the small portion of the frequently used parts of your program and data. When your program accesses a value in memory, it first looks in the cache. If it finds it in that cache, then it copies it to the CPU. If it doesn't find it in the cache, it goes out to RAM, brings a line of memory, or something between 32 and 64 bytes on the Intel system, usually 64 bytes, and brings that into the cache and then copies what you want into the CPU. If you need to access that again, the line will be in memory. We call it a cache hit when the information desired is found in the cache, and a cache miss if it has to go out to RAM to get it. Since the cache is faster than RAM, you want a high hit rate. Here's an animation of how cache works in action. Okay, we start with 4 words of cache, which is 2 lines of 2 words. And our RAM is only 16 words, indicated with addresses from 0 to F and hex. When the CPU wants address 2, it's not in the cache at the beginning. There's nothing in the cache. So it goes out and copies lines 2 and 3 into the cache. These two words have addresses that are very similar. The address for 2 is 0010, where the address for 3 is 0011. They differ only in the rightmost least significant bit. And then, since it wanted byte number 2, it copies that into the CPU. If it wants address 3 already in the cache, it can get it immediately. If it then requests address 9 is not in the cache, so it copies it from memory into the cache and then into the CPU. If you want to write address 3, then it will write from the CPU and change the value with write back technology. It doesn't change the value in RAM until it needs to. So now at this point, the cache is called dirty, or it differs from the value in the RAM. Now we want to access address E. So it'll change the 89, was the least recently used cache line. We had just used the 23 line. We hadn't used the 89, so that the 89 is replaced, and that value is copied to the CPU. Now we want to read address 4. Well, it's going to use the 23 line because we just used the EF line. But the 23 line is dirty. In other words, it's been changed, so it has to get that back to memory before we read the line from RAM, that value into the CPU. You want a high hit rate, so it will be able to get the information it needs in cache instead of going to the RAM. The hit rate, again, is just that percentage of time that it finds the information it wants in the cache instead of finding it in the RAM. You can then calculate the time it takes to get a piece of information from RAM on an average basis based on the hit rate. So here the hit rate is the variable H, C is the time to access the cache, and M is the time to access the memory or RAM. And the average access time is the hit rate times the cache time plus 1 minus the hit rate, or the miss rate, times the memory time. In our example below, we'll say you could access the cache in 6 nanoseconds and the memory in 60 nanoseconds, and you got a 90% hit rate. So the access time is 90% or 0.9 times the 6 nanoseconds plus 1.09 or 0.1 times the 60 nanoseconds memory, and that calculates out to 11.5 nanoseconds. So you notice that it's significantly slower than the cache hit rate, even with a 90% hit rate. So high hit rates are important. Most systems have separate instruction cache and data cache, and most systems have 2 levels of cache, sometimes 3 levels. So if you're accessing an instruction, then it will look in the instruction cache, starting in level 1. If it doesn't find it in the level 1 instruction cache, it looks in the level 2 cache. Usually the level 2 is a combination of instruction and data. And if it doesn't find it in level 2, it goes out to the memory across the bus, brings back a line of memory, puts it into level 2, puts it into level 1, gives it to the CPU. Similarly, if you're looking for data, it will look in the level 1 data cache, and then in the combined cache, and then into RAM. Virtual memory works in a similar manner, but at a lower level in the hierarchy. Virtual memory works between RAM and disk. It divides the memory into pages. In the Intel system, pages are generally 4K, or 4096 bytes. The nice thing about virtual memory is the operating system can put your program anywhere. Just pick a bunch of bytes, and then the location in the memory is mapped by the page table. Here's an example. We have a page table. The numbers inside the table indicate the physical location of that part of the program, with the numbers to the left represent the virtual or page numbers. So if you wanted to access something on page 1, it's really located in page 4 of the system. If you want to access something on page 4, it's really accessed in and page 7 of the system. So the page table keeps track of where things are. The system has to map between virtual addresses, or the program addresses, to physical addresses every memory access. That's every instruction fetch and every time you go out to get data from memory. So it has to do this very quickly, and it uses the page table to map between virtual addresses and physical addresses. The upper bits of the virtual address represent the page number, and the lower bits tell you which byte in the page number you want. We often refer to this as the offset in the page. So here's an example. The page number are the upper bits, and the offset is the lower bits. Now, if you have a 4K page, the log base 2 of 4K is 12, so there are 12 bits in the offset. So if you take an address like 3C90 in hexadecimal, the lower 12 bits, C90, are copied to the physical address, and then the 3 is used as an index in the table. The address there in the table is concatenated at the beginning of the offset, and then you have the physical address. You always divide the address based on the log base 2 of the size of the pages. So if you had 4K pages in the previous example, you'd have 12 bits in the offset. The upper part of the address is the page number. The number of bits in the page number would depend on how big the address field is. If you had a 32-bit address, then the lower 12 bits are the offset, then the upper 20 bits, 20 being 32 minus 12 is 20 bits of the page number. Virtual memory is an extension of paging where not every page is in RAM. Only the pages the program needs at the time are kept in RAM, and the other pages are stored on disk. When the program goes to access a page, it checks the residency bit on the page table. If the residency bit is set, then the page that you want is in memory, and it creates the physical address as indicated earlier. If, though, the residency bit is clear, meaning that page is not in memory, then it will cause an interrupt, and the operating system will get control, and the operating system is responsible for finding a place in memory to put that page, updating your page table, and then having your program execute again at that instruction so it will find the page it wants. Here's an example of splitting the address apart and then putting it back together in the physical address. So the offset, or the lower log base 2 of the page size bits, are copied to the physical address. The page number is used as an index into the page table, the residency bit is checked, and then the frame address from the table is copied to the upper part. There is a cache for this page table called the look-aside bus, and the look-aside table is just a special cache for page items. Caching and virtual memory use the memory hierarchy. If you remember the memory hierarchy, the stuff at the top is much faster than the stuff at the bottom. It's also more expensive and you have less of it. As you access a data item, virtual memory and caching moves the information up the memory hierarchy, so it'll be available in the high memory should you access it again. It also moves larger pieces, not just the bytes you want, but pages or lines of information up the hierarchy. This works with the concept of temporal locality. If you access a memory location, you're likely to access it again. So as it moves into the higher memory, if you access it again, it'll be in the faster memory when you want it next time. Spatial locality is if you access a memory location, you're likely to access nearby memory locations. That's why both caching and virtual memory move larger chunks of memory up the hierarchy. And virtual memory moves a page, or maybe 4096 bytes, from the disk into the RAM, whereas caching it moves a line, maybe 64 bytes from the RAM into the cache. So if you access nearby memory locations, they've already been loaded into the faster memory, and the system will access them much faster than if they were in the lower memory. On the second exam, you can expect questions asking you, what is the proper memory for an application? You'll also probably have an average memory access time equation. There'll be microcode for an instruction, and you'll have to simplify digital logic expressions. Good luck on all of your exams.